Welcome back, everybody. And as you can see from the slides here, the topic this week is many-body perturbation theory, which is one of our first approximations. It's a widely popular one beyond Hartree-Fock. Now, I made a recording of the lecture from last week. I was a little bit delayed. And there are some things which I wanted to pick up from that lecture and just bring them back again. And there was also a typo in expansion, a Taylor expansion. Instead of epsilon1 minus epsilon2, I had epsilon1 plus epsilon2. So I'm just going to correct that one so we have everything set up correctly. Because that simple example, which I have in the video from last week, is something which allows us to gain an intuition about what many-body perturbation theory is. So many-body perturbation theory, as you may have seen from that example, is nothing but a Taylor expansion around a specific energy. And the mathematics is that, but then we have a series of complications which we need to resolve in order to have a recipe which allows us to calculate contributions to the energy. So in general, if you can diagonalize, like we did with the full configuration interaction theory, then this is the method of choice. But normally the dimensionality is way too big, which means that we have to find approximations. And that means that we are going to reduce the effective Hilbert space or the full Hilbert space to an effective one. And this is normally called the effective space or just a model space. And we are going to have precise mathematical operations which link the excluded degrees of freedom with the effective one, or those which live in a smaller space. So many-body perturbation theory deals about finding a consistent recipe for projecting down the problem to a smaller space, which we can handle. And it's normally called a post-Hartree-Fock method because we often use a Hartree-Fock solution for the single particle energies. And that simplifies some of the calculations which have to be done. So you will find methods like many-body perturbation theory, Green's function theory, couple cluster theory, all the standard many-body methods which are used, they are often called post-Hartree-Fock methods. You would often use a Hartree-Fock calculation to get a better basis. So Hartree-Fock becomes a kitchen item in the many-body kitchen. Okay, so depending on what kind of recipe or method you use, you can look at this as high-level cuisine or low-level cuisine, and many-body perturbation theory belongs to the low-level methods. Okay, that's a personal bias. Now, I just wanted to bring up some of the things which were pertinent to that exercise, and we are going to look at the formal derivation of the standard approaches to many-body perturbation theory, and we're also going to look at some examples. And we are going to link that with what we did with full configuration interaction theory. Because when we discussed full configuration interaction theory, we try to link, in a hand-waving way, the coefficients you get from diagonalization to other types of many-body methods. But now we're actually going to calculate them. We're going to have a recipe which avoids, obviously, diagonalizing a huge matrix. Let's switch to the whiteboard. And the thing which I wanted to do first is actually to correct that problem which we had, because that problem is a problem I'm going to bring up again and again here. And it's going to be in one of the exercises as well. So what we had was a problem. So this is just a correction to previous week, to example in week 33 from October 25. And in that case, what we had was a simple two-level problem where we had the non-interacting energies, and then there was some interaction element which we put up. We could think of this as a single particle states. We had only two, or this could be just any type of many-body states, but where the problem is reduced to two levels. And then we have the characteristic polynomial which we want to find. So we want to set the determinant of that matrix, and we want that to be 0. And, this is obviously a very simple problem, which we have seen many, many times before. Minus lambda, so lambda is the eigenvalue, so we want this determinant to 0. And that is the classic way by which we set up the problem and find the roots of that. Now, what I did wrong in the setup of the result is that I mixed a minus sign. So the solution here for the lowest lying state, let me just set up that one, lying state, is going to be given by an epsilon 1. So we just call this eigenvalue for lambda 1. This is an epsilon 1. And now we are performing a perturbative expansion. So we have a lambda 1, which we wrote as an epsilon 1 plus an epsilon 2 divided by 2 here. And then we had a 1 plus 2 times g. And then we had an epsilon 1 plus an epsilon 2. And then we have a minus sign in front of the root. And then in that root, I actually had mixed the plus and a minus sign, because this is given by an epsilon 1 minus epsilon 2 squared. And this is divided by 2. And then it had a minus a 4g squared, plus 4g squared here. Now, and what we did then was simply to Taylor expand this square root. And when you Taylor expand it, you get an answer which looks like lambda 1. So we are simply using 1 plus x, which is equal to 1 plus 1/2 of x, sorry, not x squared. Oops. Let me just set it up properly. Plus x half minus x to the power of 2 divided by 8 and plus, plus, plus. And in this case, we are defining x. So we're just writing out this x as 2g divided by epsilon 1 minus epsilon 2 squared. And if I do that, then the answer should be, because I had written a plus, I had a plus here. I didn't see that before this morning. So that should be equal to an epsilon 1 plus this constant g, and then plus g squared of epsilon 1 minus epsilon 2. And then there is no term with g cubed. And we are coming back to that in studies of what is called Pauli violating diagrams, Pauli principle violating diagrams. And this goes in terms of higher powers of g. So this is an expansion where we simply took the exact solution and we performed a Taylor expansion of the square root. And what we are going to see is that this term corresponds to perturbation theory to first order. So we are now going to look at the interaction as a perturbation to the system. Then what you see here is going to be second order perturbation theory. This term here is going to be fourth order perturbation theory. And into third order is a cancellation of terms. And we are coming back to that in the explicit exercise. But let's just highlight these terms here. So this is going to be first order. And I'm going to use an acronym PT for perturbation theory. This term here is going to be second order perturbation theory. And this term here is going to be fourth order. And then we have higher order terms here. So I had a small error in the notes from last week. So have me excuse there. I was a little bit in a hurry when I did it, and I didn't pay attention. But this is the expansion. You get the Taylor expansion of the square root. And we are going to link that with the perturbation theory. But now we're going to bring back the expressions and the derivations of many-body perturbation theory. So let's now look at many-body perturbation theory, PT, which we are going to shorten to MBPT. And what we start with is the exact wave function. So this is a reminder of what we have on that video. So the exact wave function is given by some coefficient C0, and then we have some phi 0. And then we have a sum over all the other states where we have an orthonormal basis. So we have an I equal 1, and in principle to infinity. And then we have a C of I, and then we have this Slater determinants phi of I. And we have assumed that these Slater determinants phi of I, or these many-body wave functions, constitute a orthonormal basis, as before. So there's nothing new. And what we had is the operation of the Hamiltonian, which is H0 plus an H interaction. And this acts on the true ground state. So we are now focusing on the ground state. And we are going to make an assumption that the ground state is non-degenerate. So there's only one state which represents the ground state. So it means that we have just one state. We could have actually states which are degenerate, but this is something which we don't consider here. One can do that, but this is not the topic for this course. And in our case, this is simply given by H0 plus HI acting on psi 0. And if you remember back what we did in the derivation of the FCI equations, we looked at row by row. So if we now multiply with phi 0, which is our ansatz for the ground state, if we multiply from the left with that one, what we have then is phi 0 of H of psi 0, which is obviously equal to phi 0 of H0 plus HI with psi 0. Now then, if you look back at what we defined early in the semester, we normally have made an ansatz where these states, phi 0, are eigenstates of H0. So that's a pretty common ansatz, which is used again and again. And then we can manipulate these equations as done in the notes from last week. So if we then just remind ourselves, this is an uppercase letter epsilon. Let me try to indicate that this is an uppercase letter. So this is given as the expectation value of phi 0 with the operator of the non-interacting case normally. And then we can define, if we now subtract this term, if you look back at the equation which we have here, we're also going to make an assumption. So these are Hermitian operators. We're also going to use this assumption we had previously, which is called intermediate normalization. So this is obviously given by 1. So intermediate normalization means simply that we just reshuffle the normalization constants to other terms. So we define this one to be 1. And what we end up with then, if we look at the product of psi 0 of H0 of phi 0 here, this is now simply equal to epsilon 0. And we know that this term, that's actually equal to the same term here. And we know that the eigenvalues are real numbers. So that means that I can now, if I go back to the equation I have for the ground state expectation value in terms of the Hamiltonian, or rather the term which we have here, if I now simply subtract H0 from that, then we can define a new term, which is a little bit different from the correlation energy we had before. This is the correlation for many-body perturbation theory. So I'm going to call this delta E0 instead of delta E as we had before. And this is going to be given by the exact energy, E0, minus this non-interacting energy. And this happens then when we perform the sums here. This is nothing but this matrix element here. So this is just a manipulation of terms. We haven't done anything new. It's just plain manipulation. So I'm just repeating a little bit of what we had in the material from last week. Now, I just wanted to bring back what we did when we did full configuration interaction theory. Because in FCI, when we calculated this term, what we had then is delta E, which was given by E0 minus E0 ref. So we are going to recover this reference energy in perturbation theory as well, but it's common now to define everything in terms of the non-interacting basis which we have and the non-interacting energies, because that means that we have a calculational recipe where we know the expressions, where we know the results, and in many cases we have integrals which we can evaluate either analytically or easily numerically. So this is what we did in FCI, and when we looked at that, we had a sum over AI, so I'm just breaking it down, CIA, and then we had this matrix elements, which actually corresponded to the Hartree-Fock matrix elements, plus a AB, IJ, and then we had this coefficient Cij of AB, and then we had a matrix element AB of V of IJ, anti-symmetrized. So this is an equation which we have derived before. What you have here is nothing but the transition probability between a two-body state, a two-particle, two-hole state with a ground state. This is a many-body state. And this term here was nothing but the transition probability between a one-particle, one-hole state and the Hamiltonian. Actually, this is, we should write H here for the full Hamiltonian, and phi 0. And the reference energy which we have, just to remind you quickly of that one, that was simply phi 0 of H of the full Hamiltonian with phi 0, as you also did in the first midterm. Now, there's a slight redefinition of the correlation energy here, because we are going to start with the non-interacting energies and make an expansion in terms of those. But then we will obviously, when we reorder the terms, we are going to get terms where we have the interaction to first order, because now, if you look at the equation I have here, I have isolated the interacting term. So I'm going to make an expansion in terms of the interacting terms. Whereas here, actually, I had an expansion or an expression in terms of the full Hamiltonian. So we are going to treat this interaction term as a perturbation. And that's the name perturbation theory. It's as simple as that. So when we diagonalized, what we had then was simply the eigenvectors, which we could read off from our program. And then we obviously found this one immediately from diagonalization. So this is actually just a clumsy equation if you were to calculate the energy, because when you diagonalize, you already have it. However, what we are going to see now is that these coefficients are coefficients which we can obtain from a perturbative expansion, order by order, in terms of the interaction itself. That's the basic outline of what is coming now. So we are going to use some small manipulations now of the different equations which we have. And one of the things we are going to define are these famous projection operators, which we have seen in the beginning of the semester. And in that case, what we had is an operator P here, which is simply the outer product of this non-degenerate ground state ansatz. So this is just one. And then we have what's called the excluded space. So this defines an effective Hilbert space, which we often call the model space, or just the effective space. It's pretty common to just call this a model space. And it's a projection operator because we know that this p squared is equal to p here. And it projects out a specific component. And you can see that immediately if you now act on the exact wave function, which is a linear combination of all these different many-body states, which in our case are Slater determinants. If we act with this operator p on this state here, since these states are orthogonal to this state here, it means then simply that we project out this one. So it's actually not very difficult to see that. So if I take p acting on psi 0, this is simply given by phi 0. And then we have the excluded space, which is defined by this operator here, which is now the sum from over all the other states and in principle to infinity, but we are going to truncate that basis. And here we have a set of determinants, phi of I, or phi of I here. And it's pretty straightforward then to see that P plus Q defines the completeness relation, and that P times Q is 0, which also means that they commute. And since phi is an eigenbasis of H0, that means also that P and H0 commute. So I'm trying to put hats on these quantities. It's not always that I'm consistent. So this is also equal to 0. And that follows because if you then plug in P on H0 minus H0 times P, this is nothing but phi 0 acting on H0. And this term here, since the energies are real numbers, this is obviously just this epsilon 0. And then I have a minus, and then I have an H0 acting on phi 0 multiplied with phi 0. And you see again that this gives us simply epsilon 0. So what I get then is just an equation which results in 0 when I do the summations here. Okay, so that was just a quick reminder. And the total wave function then is something which we can rewrite in terms of these operators as a P plus Q, since this is the identity of psi 0. And if we then write it out, since we use this intermediate normalization, what we have is plus Q times psi 0. And if I then look at the Schrödinger equation, which I put up, I have now an H0 plus the interaction piece acting on psi 0, which is equal to E0 of psi 0. What I'm going to do now is just to introduce a dummy parameter, which I will subtract and add. So I'm just adding 0. So I'm going to rewrite this equation by shuffling H0 to one side and E0 to the other side, plus adding a constant and subtracting, adding and subtracting. A constant which I'm just going to call for omega. I just leave it unspecified. Then I can rewrite my equation as an omega minus this H0 multiplied with psi 0, which is then equal to omega minus E0, which is the exact energy for the ground state, plus this H interaction. So I'm going to isolate the interaction term. This is the machinery. The way I do this is because I want to have an expression for the energy in terms of only this interaction. So I'm also making an assumption that the inverse, because remember now that H0 is an operator, So when that acts on a state, we're actually going to project out some components. So this may actually lead to a matrix. But we assume now that omega minus H0, the inverse, actually exists. And I'm obviously going to rewrite that one as a 1. So this quantity here is a quantity we assume exists now. So if I do this, then I'm going to rewrite my equation as, so I can now isolate psi 0. And this is going to be written in terms of omega minus this H0. And then I have an omega, which I haven't specified yet. And E0 is just a constant. And this acts on psi 0. So everything now seems extremely clumsy because I've just rewritten Schrödinger's equation, and it looks actually less simple than what we had before. But the benefit here is that with some additional rewrite, I'm going to find a summation to infinite order in terms of this H1, which will give us the correct perturbative expansion. So one thing which I'm going to do now is to multiply from the left, multiply with the Q from left. And what we need to think of then, if you look at this expression here, of omega minus H0, we know that these two terms commute. Which means that, and since Q hat is equal to Q, since they commute, I'm actually going to write this term just as a Q divided by omega minus H0. And this is the same actually as us having Q divided of omega minus H0 times Q. And you can see that easily because if you put in this relation, which we have, this sum of I, and in principle to infinity of phi of I, so this is given by this expression here, to be more precise, divided by omega minus H0. And the phi's are eigenstates of the H0. So if you now Taylor expand the denominator, what you get then is just H0 acting on these states to different powers. So what you will get then when you Taylor expand this denominator, and this acts on these states here, then you have H0 acting on these states, and that gives us just an eigenvalue. So you Taylor expand the denominator, that gives us H0 to the power of 1, to the power of 2, etc., etc. And that simply gives us the energies to the power of 1, 2, 3, etc. And that means that when you then look at the expressions, this is why you can write this operation here in this kind of more compact way. And this, since Q squared is equal to Q, it corresponds also to this expression here, as long as the basis which defines Q is an eigenbasis of H0. If not, you cannot do what I did. Okay, so what we have then is a new expression, which doesn't look simpler at all. Actually, it looks worse. So we have minus H0, and this is acting on psi 0, which is again equal to Q of omega minus H0, and it acts on omega minus E0 plus H of I, acting on psi 0. Now, how to say, this doesn't look very promising, because when I put it back into the full expression for psi 0, this also contains phi 0. plus, and then I have this remaining term of omega minus H0, and then I just put an equality sign here. And this is multiplied with psi 0. So I have the unknown quantity, psi 0, on both sides of the equation, and furthermore, E0 is also unknown. So this looks just like an extremely stupid way of rewriting an equation which had two unknown quantities, psi 0 and E0. But let's now look at how we can solve this type of equation, because psi 0 appears as a numerator, which means that what we could do now is to assume a guess for psi 0 and then iterate the solution. So assume guess. We are going to assume an iterative approach. So on the right-hand side, we replace psi 0 with the known quantity phi 0. And then we will have an approximation to psi 0, which is our first approximation. So psi 0 here is equal to, or approximately equal to, psi 0 plus q divided by omega minus h0. And then I have omega minus E0 plus HI multiplied with phi 0. Now, how do we move from there? Now we have a new value for it. So you could think of this as being the 0th iteration. This is your first new value. And then you replace that one in the right-hand side again. So if you repeat that exercise, what you get now is a psi 0, 2, the second iteration, which now contains phi 0 plus, and now I have a q divided by omega minus h0, and this is multiplied with omega minus E0 plus HI multiplied with phi 0. But then I get a new term, q of omega minus H0. And then I have an omega minus E0 plus HI. So you have to forgive me if I forget to put hats on here. But then I have a q divided by omega minus H0. And this is multiplied with omega minus E0 plus HI times phi 0. And now I can plug this expression and I can get a phi 3. And then I will continue this to infinite number of iterations. So if I do this to an infinite order, then what I get, and then we just continue till we have an n equal infinity, which means now that we have a solution which is psi 0, which is going to be equal to a sum from n equals 0 to infinity. And then I have this q divided by omega minus h0. And then I have omega minus E0 plus HI. And this term which you see here is to the power of n multiplied with phi 0. So if you look at this structure of phi 0 for the second iteration, you see now that if you keep plugging this in, you're getting all these powers. As you can see here, you have these powers with q, and they also, we know that this h0 commutes with q. So we can then set this up as a set of multiplications again and again and again. So you see already here when n is equal to 2 here, you have this term multiplied with that one and multiplied with that one. And then we just continue. So what you have now is a recipe for starting to calculate the correlation energy. The only problem is that we have this E0 here, which we haven't defined yet. Now, if we multiply this with from the left with the phi 0 of h of I, what we get then is phi 0 of h of I of psi 0, which is the quantity we are looking after, which is the correlation energy in terms of the interacting part of the Hamiltonian. And if we do that, we simply perform this multiplication, we see now that we have an n equal to 0 and sum to infinity, and we end up with a phi 0 of hi, and this is multiplied by this term which we had for the wave function. So we have an expansion for the wave function itself, and we have an expansion from the energy which follows from the expression for the wave function. And now you see that on the ket side and the brass side, we have a known function, which is the ground state of the system. If you have more states you're looking after, if this model space contains more states, then clearly you wouldn't have phi 0, but you would have more of these states, but the expressions would be the same. So now we have a perturbative expansion for evaluating the energy of the ground state, which is now defined by a space where we have projected out this phi 0. But what you see now is that this energy, which we have set up here, contains contributions from the excluded space. So what we are going to do now is that order by order, we will get more and more complicated contributions from the excluded space. So many-body perturbation theory has also kind of intuitive physical coupling, because people can think of these different terms of physical processes. In particle physics, this has been extremely important in the whole machinery for quantum field theory, quantum electrodynamics, quantum chromodynamics, electroweak theory, and so on. But these are, people tend to forget that these are just terms in perturbation theory. So you can couple them with physical processes, but that is a small exaggeration or a large exaggeration. But it gives you an intuitive way of thinking of these different terms in perturbation theory. Okay, so now we have an expression, but it doesn't look very practical because we got rid of one of the unknown quantities, which is this, but we still have this unknown quantity. So how do we deal with that? Now, there are two ways of choosing, two common ways of choosing this omega, and one leads to one type of many-body theory, which is called Brillouin-Wigner perturbation theory, PT, and there we simply choose omega to be equal to E0. And then we have an expansion simply in terms of H1. However, we are going to get terms which will depend on E0, as you will see a little bit later. The other choice is what is called Rayleigh-Schroedinger perturbation theory. And this is the most common approach because that is going to give us terms in perturbation theory where we can calculate everything order by order via known equations and quantities. And in that case, we simply pick this omega 0 or omega to be equal to this non-interacting energy epsilon 0. So let's look at these two expansions. So keep in mind now that when we now look at this Brillouin-Wigner perturbation theory, so let's take a look at that one first. So what we have is that the correlation energy is given by E0 minus this epsilon 0. And the expansion itself then, if we look at the terms which we would get, is now given by a sum from n equals 0 and in principle to infinity. And I have a phi 0. And then I have a h of I, which is known. I have this q here. And then I have an E0. But now you see that the E0 pops up in the denominator. So even if we made this choice, which made life simple in one case, it's actually going to give us an expansion which depends on an unknown quantity. This makes Brillouin-Wigner perturbation theory less practical. You would often solve this iteratively. And it means that order by order, you would have an unknown quantity, which is the energy. But let's now take a look at this, because Brillouin-Wigner perturbation theory, as I will show you, is actually an exact representation of the ground state of the energy and the exact wave function. So what we have then is an h of I, and this is to the power of n, and this is multiplied by phi 0. So if we write it out, what we have then is a phi 0, and then I have an hi. So this is first order perturbation theory. And then I have a plus, and now I get this new term, phi 0 of h of I, and then I have a q divided by E0 minus H0 of HI phi 0. And then I get high order terms. I get a phi 0 of H of I of Q of E0 minus H0, H of I, Q of E0 minus H0 of H of I phi 0. And this just goes on. So what we see now is that the first term has the interaction to the first power. So this is obviously first order. The second term has the interaction to the second power. So this is a second order perturbation theory. And clearly the next term, which you see here, is a third order term. And you see that everything has dimension energy, because what I have here is just H, which has dimension energy. Here I have energy divided by energy. Here I have energy divided by energy squared. So all the equations have the right dimensions. Now, this is an equation which we actually can resum by using a trick, which is useful to have seen. So if we have a operator identity of A minus B, so A and B are operators, you can rewrite that one as a 1 over A. I don't know if you've seen this identity here before, of B, of A minus B. So what we're actually going to do now is to rewrite the denominator in terms of this expression. And this is something you can easily see if you multiply from the right with multiply from the right with A minus B. Because if you do that, you see now that the first one is equal to 1. So we just get 1 equal to A times A minus B. And then I get plus A over A times B. And this is simply A over A, which is equal to 1. I don't know if you've seen these expressions. Sometimes if you take a course in linear algebra, they may present some of these expressions where, since these are operators, you could also think of A and B's as matrices. And they do not necessarily commute. Okay, so if you use that one, what we can do then, if you look at this expression which we have, this A minus B, we can now write this in an iterative scheme where we simply plug in this expression which we have here on this side. So if we do that, and this is where we stop now before we take a break. We get 1 plus 1 over A. I have a B of 1 over A plus, and then I just keep adding. So I have a 1 over B, 1 over A of B, or 1 over A plus plus plus. And this is something which I now can use to rewrite my Brillouin-Wigner perturbation theory. And after the break, we are going to link this expression with that simple 2 by 2 matrix which we put up before the break. And then you're going to see that this expression actually corresponds to an exact solution of Schrödinger's equation. So Brillouin-Wigner, in a sense, is just a complicated rewrite of, if we go back to this simple 2 by 2 problem, and we will see that after the break, is nothing but just a rewrite of this problem here. So you may ask, why have we struggled that much and rewritten the equation? But we will see the benefit of this when we don't have these simple problems. And when we move to Rayleigh-Schroedinger perturbation theory, you will then see the clear benefit, because you will have a recipe by which you can calculate everything order by order with known expressions. Okay, so what we're going to do now is to link this simple example which we have here with the Brillouin-Wigner perturbation theory. So Brillouin-Wigner perturbation theory is nothing but an exact rewriting of the equation which you get here by requiring that the determinant is equal to 0, which means essentially that you're solving the equations for the characteristic polynomial. So, but let's go back to the manipulations which we did before the break and see if we can find a more compact expression for Brillouin-Wigner perturbation theory. What we did here was simply to rewrite this in a very brute force way by term, but we can sum up these terms and get a very compact expression. So if we use this formula which we have, this operator identity, we can then identify the following quantity. If we now look at a quantity like this, so the parameter which I'm plugging in here, which is called E, is just a number which we have, but I can rewrite this one. So this contains now the interaction term. I can use this operator relation, which I had, and simply rewrite this in terms of Q, and then I have this term 1 over E plus 1 over E, and now I have Q of HI Q 1 over E. So if you go back to the expression which we had here, what I'm doing now is simply to take this expression, I'm using this one, on this term here. And then what I get then is simply just a new set of terms where I have the interaction to higher and higher order. So I get an HI times Q, 1 over E times, and then I have a Q, a new Q of HI of Q of 1 over E, and this just goes to infinite order multiplied with Q. And if I look a little bit more carefully at this expression, and I now have also introduced the fact that this E can just be a number or an operator which commutes with Q. And I know that Q times Q is equal to Q itself. I can rewrite this term here as a Q over E plus a Q over E here, multiplied with HI times Q over E. And then I have a Q over E of HI, and then I have this Q over E, HI, Q over E, and etc., etc. And if I identify this term E with E0 minus H0, which I had in the denominator for Brillouin-Wigner perturbation theory. And if I also use the fact that the Q then commutes with this E, then I can actually rewrite the whole equation as follows. So I get a delta E 0, which is now given by a first order term of HI of phi 0. So this is just the term which we had from before. If we look back at the expression which we had this term here. But now what I'm doing is to manipulate these terms which you see here. So this term is just unchanged, but then I have all the other terms which I can simply now lump together into a phi 0 of HI of Q, and then I have a denominator with E0 minus this H0, so I should put hats again. I tend to forget that. Minus Q of HI of Q of HI multiplied with phi 0. So these are the higher order terms. Now, does this make any sense at all? Let's now go back to the simple example we have. As an example of, so what we have here is actually an exact rewrite of the Schrödinger equation. It looks extremely clumsy. But let's now go back to this simple example. Now, people use Brillouin-Wigner perturbation theory, and it's often used in an iterative way, where you start with a guess with E0, you calculate a new E0, and then you keep iterating till this E0 doesn't change. But you have to, since the matrices which you have to deal with here can be pretty large, because Q is now the spans over all the state in the excluded space, and that can be enormously large. So that means that you actually have to evaluate these as matrices, and that can be a pretty large quantity. So at a certain point, it becomes not so practical. And that's where Brillouin-Wigner perturbation theory gets replaced by Rayleigh-Schroedinger. But let's look at the simple example. So in that particular case, what we did now was simply to set up a very simple case where we had H of phi 0, which we calculated to have an unperturbed or non-interacting energy plus this constant interaction G. So this was the expectation value, and now I write this a little bit sloppily like this. So that's the expectation value of H0, and this was just the expectation value of HI. Then I had similar matrix elements I had on the non-diagonal. So this is just a two-level system of phi of I. This is now given by G. And finally, I had a phi 1 of H of phi 1. I should have used epsilon 0 instead of epsilon 1, but in the example, I just 1 and 2 because I labeled this as level 1 and 2, but I've labeled the state as phi 0 because I tend to call the ground state of phi 0. So this is equal to epsilon 2 plus G. Now, the matrix which we then had, if we also now look at this case here, if we now want to plug this in, then we know that this Q is nothing but phi 1 multiplied with phi 1, because there's only one excluded state. So if we now implement this simple model using Brillouin-Wigner perturbation theory, what I get then is simply a delta E 0, which is this E0 minus E1, and that is equal to phi 0 of HI phi 0. So I'm just taking the expression which we put for the correlation energy, and we have evaluated this one. This is just G. And then I'm plugging in the higher order terms. So what I get then is a term which now runs like, so if we look at this expression which we have here, we now need to plug in phi1 here. We will also have phi1 here, phi1 here, but then we have phi0 here. So if we look at this expression here and start plugging in the different elements which we have, this one, and that one, what we get then is the following. So this is going to be equal to phi0, hi, and then we have phi1, and then I multiply with phi1. This is my operator Q, which I had. Then I have now a denominator here, which I have to, where I have to insert. So I have an E0 minus an epsilon2 in this case. And then I have to subtract, and I should see less. Let me see if I can squeeze it in, h of I of phi1. This is then multiplied with phi1. And again, it's multiplied with phi1 of hi of phi0. Now, in this simple model, this was just G. This guy here is just G. And this guy here is just G. So if I collect all these terms, what I'm going to get then, when I switch, I plug this one over to the other side, I get now the following expression. So I get an E0 minus this epsilon1 minus G. And this is equal to, since I have now G times G, so I get a G squared. And then I have an E0 minus epsilon2 minus G. And then I multiply away the denominator and subtract G squared from the right-hand side. So what I get then is simply now E0 minus epsilon1 minus G multiplied with E0 minus epsilon2 minus G minus G squared equal to 0. Okay? If I go back to the original problem, I have the determinant. So E0 was the same as the lambda, which we had in the beginning. So we had an E0 minus epsilon1 plus G, epsilon0 minus epsilon2 plus G. And this is just the same. So Brillouin-Wigner perturbation theory, for the simple case, and you can actually, if you want to make life more complicated, you can do that for 3 levels, etc., etc. But you see now that what we got here, this compact expression, which we have here, is nothing but a rewrite of the exact Schrödinger equation, but we have a calculational recipe. Now, since we don't know E0, this is not that practical. And this is where Rayleigh-Schroedinger perturbation theory is the kind of standard approach in many-body physics. So if we now look at the Rayleigh-Schroedinger perturbation theory, or just RSPT. So in that particular case, we are going to plug in the non-interacting energy for the whole system, epsilon0. And if we then look at the energies which we get, this correlation energy, this delta E0, this is going to be equal to obviously E0 minus this epsilon0, which again is equal to this infinite sum which we have, but where we now replace omega with epsilon0. So if we do that, what we get now is simply this sum, n equals 0 to infinity, and then I have a phi0 of hi, and then I have a q divided, but now I have epsilon0 minus h0. So in the denominator, I have something which is fully known. And then I am multiplying this with hi minus, but now I'm still stuck with E0, but I can rewrite this one as a delta E0. And this is to the power of n. And the, just a moment, what did I do wrong? I think I was a little bit too fast here. No, no, that's the correct term. That's the correct term, yeah. And this is multiplied with phi 0. Now, if you look at this more carefully, this is going to be a more useful expression than what we had with the Brillouin-Wigner perturbation theory. But there is obviously an unknown quantity here, this delta E0. Now, the only difference now is that the unknown quantity appears in the numerator, which means that I can try a iterative approximation, as we did before. So the problem with the Rayleigh-Schroedinger perturbation theory is that the unknown parameter actually appears in the denominator. But since I have this in the numerator, then I can actually start an iterative process. There's also another thing which is useful to observe. So if I write this out now, so what I get now is a delta E0. So the first term is just going to be given by n equal to 0. So that's going to contain phi 0 of hi of phi 0. What I'm going to do now is simply to isolate terms with the higher and higher orders of h in delta E0. So if I then look at the next term, and there is an intermediate thing which we need to use. If I look at the delta E here, which appears from here, so I'm going to get repeatedly terms where I'm going to have delta E0 acting on Q, and Q acting on phi 0. So I have a term Q here, which acts on delta E. Delta E0 is just a number. So that means I can shuffle that over here. So that means that when I have a Q here acting on phi 0 in this expansion, which you see here, then the last term is going to disappear because this one is exactly equal to 0 because Q is orthogonal to the model space which we have chosen. So if I use that, then you see immediately that to second order, there is just going to be a term which goes like phi 0 of hi, and then I'm going to write Q here, and then I have epsilon 0 minus h0 multiplied with h of I times phi 0. Because the term which goes like delta E0 here, when n here is equal to 1, so the first term is just this one. When n is equal to 1, then I just have Q acting on hi, which gives us this term. But then there is also Q acting on delta E0, which is just a number. And that acts on this state phi 0. So this term, when n is equal to 1, which is this term here, that gives us 0 immediately. Then, if I look at the higher order terms, which are popping up now, I'm going to get a new term where I get phi 0, and I have h of I of q of epsilon 0 minus h0. But now I have to be a little bit more careful because I will get an h of I minus delta E0. And this is multiplied with a q of epsilon 0 minus h0 of h of I multiplied with phi 0. Now I cannot escape this term delta E0 because now in this term I have n equal to 2. So you will then see that when I go order by order, I'm now going to get terms which will contain higher and powers of hi minus delta A0. And these are the terms which I'm now going to rewrite, because you can now think of delta A0. If you want to stay, because if you look at this term here, you have the interaction to third order. So you have 1, 1, 1. So this is a third order term. So what I can do now is simply to plug in the expansion here again. So I regroup everything in terms of orders of h of I. So what I would do then, I would then regroup. So this is just a rewriting of this expansion, where I now simply plug in the first order term here into that one. And that gives me an expression to third order in hi. But then I will clearly have higher order terms, which then go into fourth order, fifth order, and so on. So that means that I obviously have to put pluses here. So because this just goes on to infinite order. So I can now regroup everything, and I can define a delta E0, which is now just given by an expansion in terms of I equal 1 and in principle to infinity. The most popular many-body perturbation theory approach is second order because it's simple to evaluate. And it has a name of the Swedish physicist called Möller. It's called Möller-Pleset perturbation theory. And you may have heard that name before. So this is just going to give us a delta E0 of I here. And it's pretty straightforward when you look back at this equation, that delta E0 of 1 here is simply given by the first order term in the interaction. So we have an expansion in terms of powers of the interaction. And keep in mind also that if I add epsilon 0 to this, so epsilon 0 plus this delta E01, that is nothing but our old well-known friend, the reference energy. So in many-body perturbation theory, you often start with a non-interacting basis, with the assumption that this can be a solution to a simpler problem and a meaningful solution, meaningful in the physics sense. If we then look at the next term, delta E0, which is the second order term, this is now simply given by a phi 0, and later we are going to actually decode this and rewrite it in terms of the relevant quantities. So when we've done with the general expressions here, we are going now to look at how we can evaluate this specific term to second order. Then this continues, and we have a delta E0 free. And now I'm going to write this in a more sloppy way. So I'm skipping phi 0, because phi 0 is the only state we are going to and ending up in. So I just write this in a more compact way. And I also define an E0, which is this epsilon 0 minus H0. So that means that I'm going to have a Q of this E0. I have an H of Q of E0 of H of I. But this has a minus sign, which comes from delta E. And in this case, we pick just the first order term in delta E. So we get a Q of E0. But now we have the expectation value from the first order term. So this term here is nothing but phi 0 of HI of phi 0. And then I have my Q of E0 of H of I. And this continues. So if I go to fourth order, I will have 5 terms. And then it gets more and more complicated for higher and higher orders. So this is just to be continued. Now, let's now take a look at some of these terms. And let's assume that we stop at second order. So now we are going to look at examples, but at the same time, we need to introduce these diagrammatic pictures again, because many of these terms and many-body perturbation theory is often best studied in terms of diagrams, because a diagram then says much more than just 1,000 words. Okay. So let's now assume that we approximate E0, the energy of the system now, we approximate it with epsilon 0. plus this delta E 0, 1 plus delta E 0 to second order. So this is our approximation to the energy of the system. And we know that this term which we have here is nothing but our standard reference energy. And the term which we have here, this delta E 0, is often something which we have already calculated or which we can calculate easily. So this is h of I of phi 0. And we know that this one, if we go back to what we did before, is just a sum over all these terms with anti-symmetrized matrix elements. Anti-symmetrized. So this is something which we have already calculated, typically, or can easily evaluate in terms of these integrals if they are easy to set up. So the term which we're going to take a closer look at is actually the second order term. So let's now remind ourselves of some small things. So we have a delta E2 here, and that is given now by phi 0. I have an h of I, and then I have this operator Q and epsilon 0 minus h0 times h of I acting on phi 0. So let's just write it out, because now we can bring back things which we have done before. Because some of these matrix elements are things which we have calculated. So if we now also remind ourselves that this projection operator Q is simply a sum over all the states now up to infinity of phi of I, If we do that, then we can now plug that in. And what we are going to get then, when we do that, we get a sum over all the states I equal 1 to infinity in principle. And then I'm going to have a phi 0 of h of I. And now I have a phi of I of hi of phi 0. And this is divided by a denominator now. And now I have to be a little bit careful, because what I had is actually phi of I, and we have epsilon 0 minus h. And this h actually acts on this state's phi of I. So this turns into phi of I, and then I have epsilon 0 minus epsilon of that intermediate state I. So it means that my denominator here is simply epsilon 0 minus epsilon I. Okay, now if we now go back to what we had in connection both with the first midterm, but also when we did FCI and Hartree-Fock theory, we know that this correlation energy, the way we wrote it, and now I'm not putting a 0 because this is my FCI guy. What we found then is that this is given by AI. I had these coefficients which I get from diagonalization. And then I have A of F of I plus AB IJ. And then I had the coefficient CIJ AB. And then I had this specific integral, which I'm just repeating here. So this was our FCI analysis. So now if we look at what we have something similar. You see that we have a matrix element here, which perhaps could be this one, or it could be this one, depending on the type of state. If we stay with a two-body interaction only, then we can at most have two-particle, two-hole excitations here. So free-particle, free-hole, etc. will just be 0. So we see immediately that this term here, to second order, limits the type of intermediate states which we can have. So I can have either a one-particle, one-hole here, or a two-particle, two-hole. I cannot have a zero particle, zero hole by definition because I starts at 1. That's my excluded space. So just looking at these expressions here, I know immediately what kind of physical contributions comes into play. And if I go back here and use the wisdom which I gained here, I know that this corresponds to a 1 particle, 1 hole matrix element, and this corresponds to a 2 particle, 2 hole contribution. So we also know that if I now calculate these matrix elements, if I take one of these, it gives me either this one or it gives me that one. So that means that if I look at perturbation theory, these guys here are now going to be given by what you see here. And we know that these are dimensionless. These are just dimensionless quantities which come out from the diagonalization. An eigenvector doesn't have a dimension. And if you look at this one, you have energy divided by energy. So that makes sense. Okay. So let's now look at the calculations of these terms and bring back what we had before. So what we had before was actually a normal ordered Hamiltonian, which contained the reference energy plus this f of n. So we have to be a little bit careful in the rewriting now. So the two-body interaction was then normal ordered with respect to the new vacuum. So this v of n was then given by 1 divided by 4. And then I had a general sum, p, q, r, s. I had the integral, or the matrix elements, as we used to call them. And this is given by an a of p, a q, a s, and ar. Now, the reference energy is obviously something which does not contribute here. And also, we are having here, we have an explicit dependence on the interacting part of the Hamiltonian. So we are not looking at the H0 term. So that means that when we look at F, this E ref, this is not going to be there. And then we have to be a little bit careful here. Because this one, when we looked at this as an operator, that contained a sum of a P and Q. And then I had P of H0 of Q. And then I had an AP dagger, AQ, plus, and then I had the sum of a PQ, and then an intermediate state J, which is below the Fermi level. And then I had the matrix element or the integral P of J, of V, of Q of J, anti-symmetrized, and AP, AQ. Now, in our case now, the states which we are looking at, so these specific states which we are summing over, this phi, so these are many-body states, these are not single particle states. Since we are summing from 1 to infinity, the kind of contributions which we can have, since we now have a specific type of the Hamiltonian which contains at most 2 body terms, it means that these states can be 1 particle, 1 hole, or 2 particle, 2 hole states. These are the only possibilities which we can have to second order. It means also that since these states now, they will contain a particle hole excitation at least, that means that we are going to connect P and Q here, which will give an expectation value 0 if these states are eigenstates of H0. So it's pretty common in many-body perturbation. One has only to be a little bit careful, but it's pretty common to not start with a Hartree-Fock basis. You can also start with a Hartree-Fock basis, but if the basis which we have chosen is an eigenbasis of H0, this simply implies that they have delta PQ. Now, if I have particle hole states, this is not going to be the case for us. And then this term will vanish. And the only term which remains is actually this term and this term here. These are the only ones which we need to evaluate because we are now taking into account degrees of freedom which are outside the effective Hilbert space. So what we are doing now is, if you think back to this equation here, these terms, when you diagonalize, what that means is that you include terms in perturbation theory to infinite order. When we do perturbation theory, this is just a resummation of these terms in order by order in perturbation theory. So at every order, we get something which we can calculate. And you see that because we know how to calculate this one. We know how to calculate that one. And these expressions here are now simply given by the single particle eigenvalues. So everything which you see here is something which we can calculate. But in order to get this coefficient and this one, we have to do this to infinite order to get the exact expression, which you get by diagonalization. So perturbation theory to infinite order is equivalent with exact diagonalization. So what this means for us now is that the expectation values which we can have is now the case where we have a one particle, one hole state, which then simply has this operator PQ, and then I have my J, and then I have my P of J, or V of Q of J, anti-symmetrized, and then I have my operator AP dagger, AQ of phi 0. So this is something which we have already evaluated. And we know that if we now plug this in, if we look at only the operators, we have an AI dagger, AA, and AP dagger, AQ. So that means the only possibility which we have is this one. So it means that this term which we see here, if we have an intermediate state, which is a one particle, one hole state, this simply results into a sum over A and I, because we do have, at the end, we have a sum over A and I. This is this index which we put in here, which now represent, this is not the same I, this is now a many-body state, whereas the one you see here is a single particle state. So what we end up with then is a sum over these terms, and then I have my P, or my A, and J, and then I have my V, and I have my I and J anti-symmetrized. If I do this, now I have to insert this one. This is just one of the terms. Now I would have to be a little bit careful because I'm summing over here, over the states. I also have this element, but this element is just the emission conjugate of that one. But then I have a denominator. So my denominator here is now given, so this I have to, this epsilon I is going to be given by the epsilon A plus the epsilon 0, but then I subtract the whole state I. Then my denominator has epsilon 0 minus this epsilon I, so these two i's are not the same, but this becomes equal to little epsilon A minus little epsilon I. And if I collect all these terms, what I get then is that the term with the one particle, one hole intermediate states if I collect everything, what I'm going to get then is a contribution to delta E0 to second order, which simply reads Aij, and then I have my matrix elements or integrals, which go like A of J, of V of I of J squared. And these are anti-symmetrized elements. And then I have my single particle energies, epsilon I minus epsilon A. Which again means that if I now write this out, I have a sum over A and I and J. And if I just write it out now, I have an I, J, V, A, J. And if I keep that one, epsilon I minus epsilon A multiplied with the AJ Vij. And now I can identify this as the coefficient which I had, Ci, to second order. So it's not the same as CIA from FCI, but this is my approximation which I would get from many-body perturbation theory. Then the next step is obviously to look at the possibility from the two-body part of the interaction, because we rewrote it, normalized to a specific vacuum state. We rewrote it in terms of this f of n and this v of n. And then we know that this part here, as we did when we run this calculation for FCI and Hartree-Fock, etc., this part here can only connect a two-particle two-hole state. And this is what we will pick up tomorrow. So when we look at the two-particle two-hole state, this is going, I'm just setting up the result, but tomorrow we will derive it. So we will get a delta E0, 2 here, which is now going to have a sum over AB Ij. And then I'm going to have an Ij VAB. And then I have an AB Vij divided by epsilon I minus epsilon plus epsilon j minus epsilon A, and these are the single particle energies. And in our case, this term which you see here, which is dimensionless, this is our approximation to Cij AB from many-body perturbation theory to second order. And this is not the same as Cij AB from the FCI calculation. Unless the interaction is very weak, then they can be pretty close to each other. But this is essentially now the approach which you would use. You can go to higher and higher orders. There's obviously a limit because you get more and more terms. And typically people stop at third and fourth order. That's the practical implementations of many-body perturbation theory. Sometimes you don't know whether the theory converges or not, unless you sum to infinite order. But you're hoping that order by order, the terms become smaller, but there is no guarantee. So you see the basic recipe and how you can link this to FCI, which represents the exact diagonalization. So here you have a recipe where every single term is something you can calculate or tabulate. So with these expressions here, if you have calculated this integral and put them in a table, then you would simply send in the indices like you did when you wrote the Hartree-Fock code, and then find the right elements, and same with the single particle energies. And as we will see tomorrow, this is something which we can actually rewrite in terms of compact matrix multiplications. Because A and B can be turned into a particle-particle configuration with one index, where you simply have a pointer which points to A and B. And then you can have a configuration for two hole states. And then you can rewrite this as a matrix with a subscript for particle state and a hole state. And the same here. And then you can rewrite this as matrix multiplications, which often give a very compact way and also numerically efficient way to calculate these terms, because it's numerically inefficient to sum over all the four indices. It's actually much more efficient to set up a matrix and then perform a matrix multiplication. Because you see that this can be rewritten as a matrix which I have an index J and an index I, and this could be an index A times I here. And then you sum where A collects A and B, and I collects I and J here. And this is different. This matrix here is different because that one contains also the single particle energy. Okay. So we stop here.